Now, what about carbon-based nucleophiles? So the most common carbon-based nucleophile that we've learned about is the Grignard. And we'll just go through this briefly because we covered this in the aldehyde and ketone chapter. But Grignards, of course, we've already seen, can easily do 1,2 addition to a carbonyl. Which then gets protonated, giving us our product. What if we tried to do a Grignard addition 1,4? Well, the basic answer is it won't work. Because in order for this step to be reversible, the leaving group would have to be R minus. And R minus is about the worst possible leaving group that you can have. So the 1,2 addition step in a Grignard addition is not reversible. And since it's not reversible, that means that only 1,2 can occur. Of course, that brings up the question, what if you wanted to do 1,4 addition of a carbon nucleophile? Well, what it comes down to is that you can't use a Grignard reagent. You'd have to use a completely different reagent. And so the way that we do 1,4 additions, or I should say the most common way that we do 1,4 additions of carbon-based nucleophiles, is to use an organo-copper reagent. Typically, you have to make these. You start with an alkyl lithium, so basically a carbon anion, and you add that to copper iodide. And that makes your organocuprate. And if you then add your cuprate to a conjugated carbonyl, you will end up with the 1,4 addition product. Now, there's another very, very important carbon nucleophile, which is, seen with aldehydes and ketones. And that gets us into a reaction known as the Wittig reaction. The Wittig reaction, Wittig shared the 1979 Nobel Prize in Chemistry for this reaction. You may recall we mentioned that year before. That was shared with H.C. Brown, who won for hydroboration. But a Wittig reaction allows us to convert a ketone or aldehyde into an alkene. So two basic parts to this reaction. The first is that starting with triphenylphosphine, we have to make the Wittig reagent. And this first step is pretty straightforward. The lone pair on phosphorus attacks an alkyl halide in an SN2 reaction. And then if we add a sufficiently strong base here, we can remove one of the protons on carbon. And we end up with this rather interesting looking species that has two atoms with opposite charges right next to each other and is known as an ylid. Now, depending on the ylid that you use for this reaction, some ylids you have to make in this type of reaction, and some ylids, it turns out, are so stable you can actually buy them. Regardless, the ylid is the key piece that is going to react with the carbonyl to do the reaction. So here's our carbonyl, and we can also draw a resonance form for this ylid. It looks like that. But regardless of which way we draw it, the carbon has partial negative charge, phosphorus has positive charge to it, and so the carbon can function as a nucleophile, attack the carbonyl, and then the pi electrons of the carbonyl attack the phosphorus. And that gives us this four-membered ring. This four-membered ring here is known as an oxaphosphatane. And from here, the four-membered ring can break down in a different way from how it formed. And that gives us our alkene plus triphenylphosphine oxide. But what we see in a Wittig reaction overall is that we get a new alkene that's formed between the carbon of the ylid and the carbon of the carbonyl. So this, of course, would be the simplest possible ylid that we could form. But depending on the ylid you make, this reaction can be, a lot more complex. And one of the more common types of Wittig reactions is to start with compounds that look like this. So very similar to what we had here, but now the carbon that's bonded to the phosphorus is also bonded to a carbonyl. Turns out that that proton in between the phosphorus and the carbonyl has a pKa of about 8. So very, very acidic. To put in perspective, that's pretty similar to a carboxylic acid acidity. Acetic acid has a pKa of just under 5. And so it's really easy to remove that proton to form this ylid, or this type of ylid. And this is an example of an ylid that is, so stable that you can actually, make it and stick it in a bottle and, sell it, and it'll sit around for, sometimes for years and still be stable. Once we add it to a carbonyl, though, we get the exact same reaction that we saw previously. We'll do an aldehyde in this case, but the reaction's the same. Carbon of the ylid attacks the carbonyl. Pi electrons attack back toward the phosphorus. Again, this is going to give us our four-membered ring as the intermediate, and that four-membered ring can break down to give us our product. And this reaction will always prefer to give us the transalkene because it's more stable. But you can also start to think about how powerful this reaction is in terms of synthesis. You start with a carbonyl. We've made a new carbon-carbon bond here. Again, we're forming a new bond between the carbon of the carbonyl and the carbon of the ylide. But now, if you need to keep going, you've got an alkene, so you've got all the reactions of alkenes available to you, and you've got an ester. Now, we haven't learned reactions of esters yet, but as we'll see coming up soon, there's a large number of different things that you can do with esters. And so the Wittig reaction for synthesis ends up being a very, very powerful reaction that leads us in a number of different directions. All right, the next type of addition I want to talk about is fairly brief. And that's because it's mostly review. What if we wanted to add hydrogen? Well, 1,2, we've already learned how to do that. We learned that in the alcohol section. So if we want to do a 1,2 addition of hydrogen, we've already learned that we can do that using sodium borohydride or LAH. That'll give us our 1,2 addition, and it reduces our carbonyl to an alcohol. But we can't do 1,4 in this way, because H minus, just like R minus, is a terrible nucleophile, or a terrible leaving group. And so this step here is completely irreversible. But what if we wanted the 1,4? Well, it turns out it's pretty easy to do, although it's not actually a 1,4 mechanism. So if we want to do a 1,4 addition of hydrogen, what it would look like is this, adding hydrogen here as well as here. And turns out we don't need a new reaction to do that. We already know how to do that reaction. That's just a hydrogenation. So we don't really want to call it a 1,4 addition because it's not a 1,4 addition in terms of its mechanism, but for the purposes of adding hydrogen, it looks like a 1,4 addition.